Oh, hi. In this video clip, I like to illustrate the application of statistical thermodynamics to determine some thermodynamic functions. For instance, the heat capacity, internal energy, enthalpy, all of those are thermodynamic functions that can be obtained if we have knowledge of the partition function of the system, right? So the things that we have discussed in class so far involve systems of distinguishable particles, right? So we were able in a different video to show how the internal energy of such system can be obtained in terms of the partition function. A real-life example of distinguishable particles are solids, right? So we may be able to determine heat capacity of solids if we know what the partition function for the system is. In particular, we're going to use a representation of solids given by Einstein, and this is known as the Einstein model for solids. In this model, and in a different video, we showed that the internal energy of the system is given by this. The internal energy is going to be the internal energy at 0 Kelvin, or the ground state energy, right? E sub 0, it's a constant, plus 3R theta over E theta over T minus 1, where theta, as was discussed in the different video I mentioned, is known as the Einstein characteristic temperature of the solid, right? So now that we have access to this internal energy, can we obtain the heat capacity at constant volume? So heat capacity of solids, maybe I want to say a constant volume, right? So starting here, we like to end up here, right? So how do we do that? Well, from this class and previous classes that you have taken in thermodynamics, you learn that the heat capacity constant volume is defined as the derivative of the energy, internal energy, with respect to temperature at constant volume, right? So what do we need? We need an expression for the energy, and if that energy expression contains dependence on temperature, then we have a way to calculate the heat capacity via this mechanism, right, or this approach. So back to our original expression for the internal energy of an Einstein solid. Well, E sub 0 is a constant, so any derivative of it will be 0. So what really matters is this part that has the T component, okay? So we can say that this is then equal to the derivative of, we can even take the 3R theta out. Well, let me first put it there, 3R theta over E theta over T minus 1 with respect to temperature, right, at constant volume. This whole thing at constant volume. Derivative with respect to temperature of this expression, which is the expression for the internal energy. You may ask, where is E sub 0? Well, it is not there because it is a constant. So the derivative of a constant is 0, so we can safely ignore it for this purpose, right? Here, and we also learned in class, and it's shown in the different video, that theta does not depend on temperature. It's a constant as well. Okay. So all we have to do is carry out this derivative. First, recognize that 3R and theta are constants. So you end up with 3R theta as a coefficient, if you wish. And then what you have is the derivative with respect to temperature of this part here, which is pretty much, right, E theta over T minus 1 to minus 1, well, with respect to temperature. And just to emphasize the physics, this is constant volume. Okay, think about it. What would be that derivative? Right? you should get a result similar to this thing here. Okay, let's see if this matches the expression that we were given at the very beginning. So we have 3r theta over t squared, so this theta and this theta goes multiply to give you the theta squared, and the t squared that is already present here, that you can replace easily with this, right? So we have this 3r theta over t squared. We see our familiar e theta over t minus 1 denominator here. So e theta over t minus 1 squared, and then e to theta t. And as you can see, my friends, this is identical to the expression that we were given at the very beginning, right? So, tricky parts. The tricky part is nothing more than the calculus associated with this derivative, right? Familiarity with this calculus needs to be there so you can recognize what's happening, right? So, other than that, it should be straightforward. It's just a matter of remembering the little rules or the few rules associated with making derivatives of functions, and when the function is in the denominator, and then the internal derivative that you have to do, if like in this case, this theta over t is coming from the internal derivative of this part here, right? So that will give you theta, and then the internal derivative of 1 over t is negative 1 over t squared. And then from this negative that should have been here, negative times negative give you a plus, so you end up with a plus quantity. Okay? So that is the derivation in short. So we talk about the limits of the heat capacity at high temperature, low temperature in class. We'll do that. So we will see what happens when t goes to infinity or when t goes to 0. And then you will find that at 0 Kelvin, heat capacity is 0. At high temperatures, heat capacity becomes a constant. Okay? So we'll discuss that in class. The purpose of the video clip was mostly to show how to arrive at this expression given this expression. Okay? Thank you.